Chemistry, we're moving on to our final unit of the course, Unit 12, and this is on a subject of electrochemistry and redox reactions, and only AP track students will be doing these assignments in this unit. So review of the activity series, we did that back in about day 40, 41, about half the class ago. So the activity series identifies which elements will react with an ionic compound to create a single replacement reaction. So if the lone element is above the cation in an ionic compound, then the lone element will pass electrons to the cation and the reaction will take place. So if iron were in an ionic bond and magnesium were the lone element, then magnesium would pass electrons to iron, and that would cause magnesium and iron to switch places. If the lone element is below the cation in the ionic compound, then the reaction will not take place. Iron will not pass electrons up to magnesium. So let's see some examples of that. So here we have zinc and two chlorines, and they're going to form an ionic bond. The chlorines have high electronegativity, so they like to pull in electrons. Zinc has a relatively low ionization energy, so it more easily gives up electrons. So those electrons, initially it has a zero charge, so those electrons will pass over to the chlorines. And what will happen then is the chlorines will become chloride ions, both with 1- charges. They each attract one electron from zinc, and if you look at your charge number by ion sheet, you see the chloride ions take on a -1 charge. Now, those two will be attracted to each other to form an ionic bond. The zinc has a 2+ charge now. The chloride ions each together have a 2- charge, and so that forms zinc chloride. That's an ionic bond. So the charge number by ion sheet indicates that zinc has a 2+ charge and the ionically bonds with 2 chloride ions, as you see there. So that goes way back to our foundations unit. Now down below, you have the zinc chloride, and now a calcium comes along. The calcium is just a lone element. It's electrically neutral. It's just a normal calcium atom, and it comes along nearby. So the zinc has a 2+ charge, the chloride has a 2- charge. So the question is this: will the calcium pass its 2 electrons over to zinc? Is zinc strong enough to pull 2 electrons away from calcium? Because if it is, then the zinc will then again become electrically neutral because it will have its full complement of electrons, and the calcium will become positively charged. That means the zinc will break away from the chloride ions because it no longer has a charge, and the calcium with its 2+ charge will go over and bond to the chloride. So the zinc and the chloride calcium effectively switch places. So a single replacement reaction will take place if zinc can take 2 electrons from calcium. So will this happen? So electrons fall down the activity series. So calcium's the lone element, and it lies above zinc on the activity series. This means that calcium will pass its electrons down to zinc, and they'll switch places. So watch how this happens. Calcium's at 0, zinc is 2+. So there goes the electron from calcium down to zinc. Now let's see it up above. These electrons pass over from calcium to zinc. Now zinc is electrically neutral. It now has all of its electrons back, whereas calcium is deficient by 2 electrons, so it now has a 2+ charge. So what's going to happen? They're going to switch places. So that's a single replacement reaction. So this movement of electrons between metals like this is going to be central to our studying of oxidation reduction reaction, redox reactions, and electrochemistry. So the zinc becomes 0 charged, and the calcium becomes 2+ charged. The zinc breaks away from the chloride ions because it no longer has a charge to hold it to the chlorides, and the calcium, which now has a 2+ charge, forms an ionic bond with the chloride. So the zinc and the calcium switch places. Electrochemistry deals with the use of chemical reactions to create electricity. This is how batteries work, in other words. The study of electrochemistry centers around a class of reactions called oxidation reduction reactions, also known as redox reactions. Redox reactions transfer electrons between reactants. Now remember, acid-base reactions transfer protons. They're referred to as proton transfer reactions, so redox reactions are electron transfer reactions. In a redox reaction, an element on the reactant side is oxidized, which means that it loses one or more electrons. The electrons are passed to another element which is reduced, meaning that it gains the electrons. So the activity series shows that electrons will fall down from zinc down to copper. So they'll do this. So in this case, zinc was oxidized because it lost electrons, and copper was reduced because it gained electrons. An oxidation number in an ionic bond is the same as the charge number. In a covalent bond, the oxidation number is the charge on the atoms if the most electronegative atom completely took the electrons away. So let's see some examples of that. So the mnemonic for this is oxidation is loss, reduction is gain. So oil rig, that picture on the right is a picture of an oil rig out in the ocean. So oxidation is loss, reduction is gain of electrons. Oxidation is loss of electrons. So in this example, the previous example, zinc is being oxidized. It lost electrons. Copper is being reduced. Reduction is gain of electrons. The copper gained electrons. So again, there's the illustration. Zinc is being oxidized and copper is being reduced. So oxidation is loss of electrons. So zinc is oxidized. Reduction is gain of electrons, so copper is being reduced. So there you'll see it yet again. Zinc is being oxidized because it loses electrons. Copper is being reduced because it gains electrons. Zinc is called the reducing agent because it is causing the copper to be reduced. This gets a little confusing, but you go through it a few times, it won't be so confusing. And copper is called the oxidizing agent because it is causing zinc to be oxidized. So an agent is something that causes some kind of reaction to happen in another thing. So zinc is the reducing agent because it's causing the copper to be reduced, and copper is the oxidizing agent because it's causing, by pulling electrons away from zinc, it's causing the zinc to be oxidized. So summary, zinc is called the reducing agent and is reducing copper. Copper is called the oxidizing agent and is oxidizing zinc. We will study a class of reactions called oxidation reduction reactions, also called redox reactions. Oxidation reduction reactions involve the transfer of electrons. The transfer of electrons uses a bookkeeping system called oxidation numbers or oxidation states. Those both mean the same thing. I generally call them oxidation numbers. Oxidation numbers are how charges are assigned to elements in oxidation reduction reactions. In ionic bonds, oxidation numbers are the same as charge numbers. In covalent bonds, oxidation numbers are assigned as though the most electronegative element took electrons from the less electronegative element. The transfer of electrons uses a bookkeeping system called oxidation numbers or oxidation states. In covalent bonds, oxidation numbers are assigned as though the most electronegative element took electrons away from the less electronegative element. In other words, it treats a covalent bond as though it was an ionic bond. So here we have an ionic bond. You have a metal calcium and a nonmetal oxygen. Calcium takes on a 2+ charge. It passes electrons over to the oxygen, which then takes on a 2- charge. And then the 2- and the 2+ attract each other to form an ionic bond. So there the oxidation numbers and the charge numbers are the same in an ionic bond. So calcium, a metal, has a charge number of 2 plus, and oxygen, a nonmetal, has a charge number of 2 minus. They form an ionic bond where calcium becomes a cation and oxygen an anion. Now here we have a covalent bond. It's between hydrogen, gas, and oxygen to form H2O to form water. Okay, so now what we have is we have charge numbers on these. So hydrogen has 2 1 plus charges, and oxygen has a 2 minus charge. Now we know that H2O is not an ionic bond. The oxygen does not totally pull the electrons away from the hydrogens. However, it does. It's polar covalent, so it does pull the electrons toward the oxygen. So what we're going to now do is assume that oxygen did actually take the electrons away from hydrogen. So it becomes a -2 charge, and the hydrogen becomes a +2 charge. So we treat a covalent bond as though it's ionic, and as though the most electronegative element here, that would be oxygen, totally pulls the electrons away from the least electronegative element, hydrogen. So let's read this. Water is a polar covalent molecule, so oxygen does not take 2 electrons away from hydrogen. However, since oxygen pulls the electrons closer to it, it has an oxidation number of -2, and hydrogen has an oxidation number of +2. Note that charge numbers place the plus or minus sign after the number. That's the way we've been writing charge numbers since almost the beginning of this course. But oxidation states or oxidation numbers place the plus minus sign before the number. So you notice the calcium oxide up above versus the H2O down below where the plus and minus signs are. Okay, so here's an example of a redox reaction. So let's look at this, and let's look at the rules. An oxidation number is given to each element in the compound, not to the entire compound. So you notice every element up above has a charge number assigned to it. And that's multiplied by the number of atoms that it contains. So it is individual elements that are being oxidized and reduced, not an entire compound such as MgCl2 or HCl. It's each element you look at to whether it's oxidized or reduced. Reduction gets its name because although electrons are being added to the element, they are negative. So the oxidation number is being reduced. So that may clear up something you might have been wondering. Why do you say when electrons are gained that element is being reduced? And that's because it's gaining negative signs. It's like if I say 3 plus -1, that takes the number from 3 down to 2. So by adding a negative, you reduce the number. So by adding a negative, which is an electron, to an oxidation number, then that reduces the oxidation number. So that's why you say when something gains electrons, it is being reduced. Only 2 elements in a reaction are oxidized or reduced. In this reaction, the one up above, chlorine's oxidation number does not change. So it's 2 times 1 minus on one side and 1 minus times 2 on the other, so that's -2. It does not change. It's a spectator, remains aqueous. But look at magnesium. Magnesium starts off on the reactant side as a 0 charge. It's just a normal magnesium atom. And then when it gets over to the product side, it becomes Mg2+. So its oxidation number increased. And that means it was oxidized. It went from 0 to +2. It went up. Now look at hydrogen. Hydrogen starts off at 2 times +1 over on the reactant side on the left. So that's a 2. And then by the time it gets over to the product side, it becomes an H2, and H2 is a pure element in its most stable form, so it's going to have a 0 oxidation number. So its oxidation number was reduced. It went down. It went from 2 down to 0, so that's a reduction. So this reaction can be broken into 2 half reactions. So this is just simply a zinc based on the activity series is going to transfer 2 electrons over to a copper ion. Copper is below zinc on the activity series. So zinc is electrically neutral. It has a charge of 0. The copper has a 2 plus charge, so its oxidation number is +2. And then by the time this is done, the zinc will have passed 2 electrons to copper. So now zinc is +2 and the copper is 0. So if you look at that, zinc is being oxidized, because its oxidation number goes up, and copper is being reduced because its oxidation number is reduced. It goes down from +2 to 0. So this reaction can be broken into two half reactions as follows. Half reactions show the electrons gained or lost by each element. So first we look, there's the overall equation. Now we just look at the zinc part of the reaction. So what has happened to zinc? A normal zinc atom gave up 2 electrons. So it becomes a zinc 2+ ion plus those 2 electrons which went over to copper. So that's the oxidation half reaction. The oxidation number of zinc has increased. Now we look at the half reaction involving copper. Copper starts off as a 2+ ion, and then it gains 2 electrons, so that over on the product side then it becomes a normal copper atom, just Cu. That's the reduction half of the reaction. The oxidation number of copper was reduced from 2+ down to 0. Here are the rules for assigning oxidation numbers. You'll be giving a copy of this. They seem a little bit involved, but don't worry. They're not as hard as they seem. So 1, elements in their elemental form, most stable form, have an oxidation number of 0. So hydrogen, just a hydrogen atom by itself, has an oxidation number of +1 when it's bonded to nonmetals. But if you put it together with another hydrogen to form a hydrogen molecule, that's the most stable form for hydrogen, so that has an oxidation number of 0. 2, for monatomic ions, the oxidation number is the same as the charge number. So if you look at your charge number by ion sheet, potassium, K, is a +1, oxygen is a -2, so that's going to be the charge number is going to be the same, the oxidation number is going to be the same as the charge number. 3, nonmetals usually have negative oxidation numbers, but they can be positive. For example, sulfur can have an oxidation number ranging from -2 all the way up to +6. So it can have a whole range of oxidation numbers. And A, hydrogen has a +1 when bonded to nonmetals and a -1 when bonded to metals. Almost always hydrogen will be bonded to nonmetals. So there you see that. That's usually the one you're going to see as hydrogen has a +1. Oxygen always has a -2 except in peroxides such as H2O2 where it is a 1-, but you're almost never going to come across a peroxide. So oxygen is always a -2, and we're going to call that the anchor. Whenever you start doing an analysis, and you'll see examples of this in just a few moments, you're going to start with oxygen and anchor that at -2, each oxygen atom at -2. Fluorine always is a -1. And other halogens are -1 except when combined with oxygen, they are plus numbers, they are positive numbers. So it's a lot, you don't need to remember this, there will be a list given to you with this on it. So let's do a couple of these. The first equation looks kind of complicated, but let's see, it's not that hard. So first of all, cadmium is an element by itself. It's a lone element, it's a natural element, so it has an oxidation number of 0. Now we go over to nickel oxide. So oxygen has a charge number of -2, and there are 2 atoms which equals -4. So there's the -2 on oxygen. That's your anchor. You always assign -2 to an oxygen. That's the oxidation number, but you have 2 of them. So you have to multiply the 2 by 2 minus to get the 4 minus for the charge number. So that's the charge number up above. So the oxidation number, which doesn't change for oxygen, is a -2, but the charge number up above depends on how many oxygens, so it's a 4 minus. So you need to make this charge balanced, just like we've always done with ionic bonds. So if oxygen, the O2, has a 4 minus charge, then the nickel has to have a 4 plus charge. And since there's only one nickel, that means the charge, the oxidation number rather, on the nickel is going to be +4. Now we go on to water. And there, water, we're going to anchor it at -2 for its oxidation number. You only have one of them, and so that means its charge number is going to be -2. Now you have 2 of the hydrogens. Ignore the coefficient. That really is not a part of this. You have 2 of the hydrogen atoms, and they're both +1s. So the oxygen is going to be 1 oxygen times 2 minus is 2 minus, and the hydrogen is going to be 2 times 1 plus is 2 plus. So now that's charge balanced. That means the oxidation number on hydrogen is a +1, and on oxygen it's a -2. Now we go over to the hydroxide, and you see that there's two of them. They're OH, and then there's a 2 outside the parenthesis. So we're going to anchor hydrogen as +1, and so it's going to be 2 because the 2 outside the parenthesis times +1 is 2+. Now the oxygen is going to be its usual -2. So it's going to be 2 times 2-, that's going to be 4-. So now when you put together what's inside that parenthesis, the 4- and the 2+, you get a 2-. You see that right above where the arrows are pointing. So if that hydroxide, that OH2, is 2-, then the cadmium, there's only one of them, has to be a 2+. So that's going to be a 2+ charge, and since there's only one of them, that means that has to be the oxidation number on cadmium is +2. Now we go over to the nickel hydroxide. You're going to do the hydroxide exactly the same way. Anchor the hydrogen and the oxygen with their oxidation numbers. Then the hydrogen again is 2 times 1+. The oxygen is 2 times 2- is 4-. So overall that's a 2-. That means the nickel has to be a 2+ to charge balance that. And that means since there's only one nickel in this compound, it has to have an oxidation number of +2. So now we're ready to see what was oxidized and what was reduced. So look at cadmium. It went from 0 on the left side of the arrow over to +2 on the right side. That means its oxidation number increased. It went up, so it was oxidized. It went from 0 to 2. So the oxidation number of cadmium increased from 0 to +2. This means cadmium was oxidized. Now we look at nickel. Nickel over on the left side is a +4, and when it gets over to the product side on the right, it becomes a +2. That number went down. That means the oxidation number of nickel was reduced. So that's the reduction. So the oxidation number of nickel decreased from +4 to +2. This means that nickel was reduced. So that's how oxidation reduction works. Nothing else, the hydrogen, the oxygen, nothing else changed its oxidation number from left side to right side. You can verify that by looking at that. Okay, in the next equation we have Cr2O7, and that's a 2- ion, meaning it has 2 more electrons than protons. By the way, that's called a dichromate ion. And you're going to add that to a chloride ion, and what you're going to come out with is chromium 3+ cation and a chloride molecule, electrically neutral chlorine gas molecule, chlorine. Okay, so let's go ahead and see how that works. Okay, so there are 7 oxygen with a charge of 2-. We always anchor oxygen with the 2-. That equals 14-. So we see that up above. 7 times 2- is 14-. The overall charge on the molecule is 2-. That's the 2- you see down there in the chemical formula. This means that the value of the Cr, the chromium, is chromium -14 equals 2-. The oxygen is -14. The overall molecule is -2. So what does chromium have to be? It's just a little algebra problem so that chromium -14 will give you -2, and the answer is +12. Since there are 2 chromium ions, then each chromium equals a +6. This means that the oxidation number for chromium is +6. So pause it and think about that for a second. You started with the oxygen. You always use that as your anchor. We have 7 times -2 is -14. The overall molecule, you can see by looking at the formula for it, is a 2-. So oxygen is -14. The overall molecule is a 2-. So what does the chromium have to be to give you a 2-? So that would be 12. 12 minus 14 will give you 2-. But there are 2 chromiums. So that means each one has to be a +6. 2 times +6 gives you that +12. So that means the oxidation number on chromium is 6. So the oxygen is -2, it always is, and in this case the chromium is a +6. Now we go over, and the chloride is a 1-, the same as its charge number. The chromium is a 3+, same as the charge number you see there. And chloride is a pure element in its natural form, gas form, Cl2, so that's a 0. So now let's go ahead and assign oxidation and reduction here. So the chromium is reduced. It goes from a +6 oxidation number on the left to a +3 on the right. So that number went down. It was reduced. So the oxidation number is reduced. That means that that's the reduction. And the chloride went from a -1 to a 0. So that's the oxidation. The oxidation number increased. And that takes care of this lesson. It's a lot to learn. I've given you enough problems to practice on. So do this, get good at this, and you'll be on your way to finishing this final unit.